Thank you to the organizers, and thank you for having me here. Probably going through some classic results. So there is, and there are many correspondence between systems of arithmetic and set theory. Probably at the lowest level, we have that Robinson arithmetic, so Peano without induction, can interpret set theory with adduction. So this is a theory that has this adduction operator. So it states that the universe is closed under this operation, extensionality, and empty set. Slightly higher up, oh, and that previous result, you can't get by interpretability. Q is not sequential theory. It does not omit pairing functions. Next, we have Peano is synonymous with finite ZF with the transitive containment axiom. This was shown to, the synonymy was shown by K. Wong, and actually the Ackermann interpretation and the inverse Ackermann interpretation can be carried out actually over a weak theory like I delta 0 plus x. And then we have Simpson's results, which will be more pertinent to at least this talk. What we have is this theory, ATR naught, which is one of the big five of reverse mathematics, is interpretable to this countable set theory known as ATR naught set. The characterizing axiom is the so-called axiom beta, or the existence of Mostowski collapse. However, we do not have synonymy here, so it's the relation is not as strong as that with PA with finite ZF. And finally, we can also, the transfinite recursion in ATR naught allows us to construct the constructible universe, which also gives us a series of interesting interpretations with set theories containing collection. Okay, so maybe just to give a quick overview, so what is going to be our system? What is going to be our interpretation? Well, we're going to be considering well-founded trees under the relation of bisimulation. So bisimulations, in a sense, capture the bare essentials needed to get extensionality. So if naively we try to maybe quotient out the universe, so sets that are extensionally equal now are equal, well, we create more equalities. So you get more sets that are going to be extensionally equal. And we need to get even more equalities, and we have to iterate this process. So as you can imagine, and in fact, ATR naught is equivalent to the existence of these bisimulations. To go over, so given any tree T, a bisimulation B on T is going to be a symmetric relation that is going to be symmetric and is going to satisfy this back and forth relation. That is, for any given node sigma and any immediate successor of sigma, if there exists a successor of tau, such that tau and sigma, the extension of tau and extension of sigma are equal under this bisimulation relation, then sigma and tau, and this is if and only if sigma and tau are related by a bisimulation. Of course, there's if you're not working with well-founded trees, this might not be unique. Okay, so in fact, we get very natural interpretations. So with well-founded trees, we can interpret set theories satisfying regularity or foundation. With arbitrary trees, and taking maximal bisimulations, we can interpret the axial anti-foundation axiom. So you can get interesting anti-foundation interpretations via this way. And then you can modify the definition of bisimulation to trees that admit labels and interpret set theories with your elements. Okay, so maybe to describe what is the, well, Simpson calls it the star interpretation, and I'll stick to this notation. So what does it mean for a tree S to be equal to a tree T? Well, if I'm given two trees, S equals star to T, what we do essentially is we're going to consider, right, the tree obtained as so. This will be a well-founded tree. And then what we ask is if this pair is in the unique bisimulation, then S will be equal star to T. Okay, it's going to be a delta 1 definition usually. And then membership, on the other hand, so we have S is in star T. Well, this will mean that, there exists some sequence sigma in T. Sigma has length 1. And what we have is that, just drawing this out, this is our tree T. Then we have our node sigma. And then we have the tree extending sigma. We'll call this T sigma. Well, this T sigma is equal star to S. Okay? And you kind of start capturing the back and forth, idea that is captured by simulation. Okay, and so Simpson uses this specific interpretation to get, the interpretation of ATR not set in ATR. Well, what about for higher order arithmetic? Well, this is a very versatile interpretation. It can be easily carried out in, nth order or nth plus 2 order arithmetic. And in that case, we actually interpret, ZFC minus, right, ZFC without power set, plus the nth power set of omega exists. But we would like to generalize this in 2 ways. The first way is that, well, we would want n to be an arbitrary ordinal, or at least some sufficiently good defined ordinal, which is preserved under inner models, for example. And then we would like to also consider systems with restricted comprehension, so to try and generalize this method. So I'll introduce the systems, and I'll write them down so they'll be available for everyone. So the first system is the system A minus. Its axioms are going to be extensionality, pair, union, infinity. And infinity is, you need to be specific because these are weak systems. And then predicative or delta 0 separation. Okay. And then we have our system B. Our system B is going to extend A and is also going to have the axioms of regularity. That states every set is internally well-founded. Regularity. Finite transitive containment and finite power set. Okay, and finally we have the system we call C, which contains axiom beta or the Mostowski collapse, right? That states that essentially that for any well-founded relation, there exists a collapsing function to that relation. That for any set, yeah, the set of finite subsets exists. And there's actually like a specific reason for this. So if you put the usual Cartesian product, you can get very nasty models. So there's the issue in Devlin's book of constructibility that Matthias had noticed that the system DB, so even if you add full foundation, you might have that the set of set of natural number, the set of sets of natural numbers of cardinality 3 or 4 cannot exist. So you get lots of pathologies which adding this axiom instead of the Cartesian product, kind of fixes out. Okay, so probably should mention it. And then for any, and here we need to be a bit careful, so for any reasonably defined ordinal gamma, so usually you can have gamma just be defined by some initial segment of the constructible universe. Well, we're going to define the system. So for any system T, T gamma is going to be the system T plus the gamma-th iteration of the power set exists. And at limit stages, we take unions. Okay. Equivalently, you could this could be substituted by V omega plus gamma exists, right? That's another alternative. Okay. So actually, it turns out A minus is disastrous as a system. So it actually needs a correction. So the first thing is that it does not ensure that ordinal addition is total, nor that any reasonable notion of addition can be compatible with the natural numbers. In particular, you can have that for any discrete linear order with minimum and no maximum, that linear order can be homeomorphic to the omega of a model of A minus. And the construction is relatively simple. What do? You grab a discrete linear order with minimum and no maximum. You take the definable elements, and then you take the closure, right? You define membership as you would expect. So on L, it's going to be given by the order on L. And between elements of L and elements in def L, it will be, true membership. So then you take this structure here and you close it under pair and union. And this, you can readily verify, will actually satisfy all of the axioms of A minus. One thing is needed, so the thing that you actually need is the fact that the discrete linear orders with the successor relation admits quantifier elimination. So in particular, it's going to be a O-minimal structure. So the reason is, why can you have the axiom of infinity and, you can actually carry out this whole construction in I delta 0 plus x. Yeah, with successors. Yeah, discrete linear order, no min and max. Min, no max, yeah. And you can then construct in this way, and then via codings, you can carry it out fairly reasonably in I delta 0 x. So the main insight is that since, these dense linear orders are going to, you can pick an especially nasty one, right? For example, the one that you have omega here, and then you have the integers here. There's no notion of addition that is compatible with this order. Furthermore, you actually have that the sequences in your model will actually only be of standard length because you're taking the standard closure under pair and union. So you cannot define ordinal addition in the regular way because you don't have enough sequences. And this example can be formalized quite low, so it is a very weak system. And the main probably insight is that you have omega, you have infinity without actually having it. This is because you're just going to have intervals are going to be your definable sets. So you will never get the actual standard cut, which would cause all sorts of issues. At that point, delta comprehension would explode, would become, you'd get to the level of AC naught. You can just fix this by adding this ad hoc axiom that the sequences on omega exist. And Emanuele had actually spot that if you do have axiom beta plus the Cartesian product, there's a very interesting way in which you can actually prove the existence of addition and multiplications as graphs, which is quite nice. Okay, so now that tangent is over, so another tangent. So what you actually want to do is now in this system A, you want to show that there are enough sequences, right? So what you want to be able to do is code sequences of elements in the P gamma omega and with elements of P gamma omega. And well, what you have at this point is maybe, right, having defined these sequences, well, maybe you want to just move to some interim system. So this will be our system B that already has, admits the construction of the sequences of a set. So, well, A gamma will not prove the existence of bisimulations in general. This is, it's actually proved. So we'll go over that later. But we can, of course, consider a smaller class of well-founded trees such that we are insured by simulation. And the thing is that if you actually look at it, right, so if you actually kind of play around with these trees, what is the tree for transitive containment and finite power set, right? These trees are actually going to be, have a lot of self-similarities within it. So the complexity needed to get a tree, that represents the transitive containment or the finite power set are fairly simple. And so we can actually restrict ourselves to, a certain class of trees. It actually has the advantage. So these trees being well-founded are a lot more simple. So if you look at the, standard definition with well-founded trees, being well-founded can be quite complicated. With these trees, you get that the complexity of formulas is preserved. And so in particular, what you get is this nice interpretation. So in A gamma plus sigma k separation, you get B gamma plus sigma k separation. And, working over B is less coding intensive, so it's also a quality of life result. And you get other things. So you can actually, well, A gamma, it actually is at the level of ACA naught. So in the system ACA naught, you can actually carry out this translation. What you are going to have is that, since it preserves complexity, what you're going to get is that if you start with sigma 1n comprehension and sigma 1k induction, you're going to get B plus sigma n separation and sigma k foundation. So by sigma k foundation, unlike regularity, this is an axiom scheme that states for any formula given by sigma k, right? Any sigma k class is going to have either be empty or have a minimal element. And I mean, you get a whole bunch of other, interpretations. So if you do the regular Simpson interpretation, axiom beta plus delta 1 separation is fairly strong. It's going to be at the level of delta 1, 1, 2 comprehension, I believe. But at this level, right, since you aren't working with you don't get axiom beta, you can get, surprisingly strong separation axioms. And you can actually carry this out over NVG. NVG can actually formalize these trees, has sufficient coding, and so you can actually interpret the system B gamma plus gamma is inaccessible. And this proves that B will not be able to prove truth predicates in particular. It's very similar to ACA naught, right? ACA naught can have, a beta model, but can't prove the consistency of, bar induction, for example. So it can prove the partial truth predicates, but it can, for any standard K, but it can't do it for everything. And we'll see actually the system C that we introduce in all cases is different in this regard. Okay, and we also get, right, we have that P gamma omega is going to be preserved, so you actually get some conservation results as well. Okay, probably should ask any questions? What should be the analog, though, to carry out the full interpretation? Well, we probably want to consider, bisimulations can be viewed as being fixed points to some, fairly simple operator. Over arithmetic, it will be arithmetically defined operator. So actually what you get is that the axiom stating delta 0 fixed points exist, right, will prove the existence of bisimulations. It might, so this is something currently working out, you might just be able to define naively delta 0 transfinite recursion the same way you would as AT or not, and that probably should get you almost everything, but that's still a work in progress. You get that already at sigma 1 separation, you can prove that there are going to be least fixed points, so that system's strong enough to prove that there are least fixed points, and we get this other interpretation. So unlike the B star interpretation I introduced before, we have a loss of complexity here, right? So the system A gamma plus sigma kappa plus 1 separation is going to go down to sigma kappa separation, and for arithmetic, this is the best you can get. There's always going to be a loss in complexity in some sort, right? You're always going to have to shift downwards. So for example, if you go from pi 1, 2 comprehension, you're going to get sigma 1 separation plus axiom beta. So for gamma equals to 0, well, going ahead. For gamma equals to 0, well, you can't do much better. And then finally, thing to notice in the system C gamma, you can actually prove once that aleph gamma exists. And this will be important because the next step in the interpretation is to make the constructible universe. Okay. But there's an improvement. So when gamma doesn't have cofinality omega, you're going to get a situation that is different. You actually can do better in the case when the cofinality of when gamma is successor or it has uncountable cofinality. Well, then actually what do we get? Well, we get the omega parts, right? The countable subsets of P gamma omega can be coded with elements of P gamma omega. Think about the reals, right? The countable subsets of the real, I can always code a countable subset of reals using the pairing function and the naturals as a single real. And this generalizes for, gamma successor or of larger, of uncountable cofinality. And what else do we have? Well, this is, if we're working with dependent choice, right? A tree will be well-founded if and only if it doesn't have a countable path. So you can actually define in a delta zero fashion relative to some coding on p gamma omega, you can determine whether a tree is well-founded. And you would just immediately get the previous results, right? You would get this result with a +1 if you started with dependent choice, like right off the bat. But we want to do better. We want to remove the need for dependent choice. So what we do is, well, or if I had a well-ordering on p gamma omega, I could also do this. But what I'm going to do now is I'm just going to consider, I'm going to construct a well-order that morally has well-order aleph gamma. Or in some cases, when in the successor case, you will not be able to do that in general, right? So just consider the system A1, right? The reals exist. There's no way you're going to have, you might not have a well-ordering of order type aleph 1 without choice, right? In choiceless settings, aleph 1 does not necessarily embed in the reals. But what you can do is you can get consider the equivalence classes of well-orderings. And actually, it turns out that the structure of this, almost well-order will be useful in the construction, in the tree interpretation. So what you can now consider, right, the domain of interpretation will be the well-founded trees on, I fixed this, large enough well-ordering. The existence, sorry, I probably should add this. The existence of such a well-ordering exists because you can iterate definably the Hartog operation. So, for limit cases, you can work in Zermelo, and in Zermelo, you actually will always have that, you can always definably define large enough well-orders. And actually, Matthias has also observed this and used it for his analysis of MacLean's set theory. But what do we get here? So we want to consider trees such that at no point will I have, so if I start with something that has order type aleph gamma, I just consider the trees on that well order. But if I'm considering equivalence classes, you're going to need a trick. The trick is this. So what you want is that you're going to have equivalence classes. So maybe I can draw it here. So I'll have my U. And these will be well-orderings on some W. And the ordering is via embedding. Okay? So what you can imagine is that this is going to be a bunch of classes which are, ordered by U. And what you want to do is take trees such that for any sequence in the tree, right, there exists a fixed n, any sequence of length more than n, what you have is that you have to commit. So any extension of it, right, it will not have two extensions containing elements in the same class. So you have to make choices after a certain point. And these, you get the strong interpretation. You won't get the existence of the power set of gamma, but you will get the existence of aleph gamma. And once you move to the constructible universe, building it up to aleph gamma will give you the gamma-th power set of omega. So once you need GCH to then make this work. Okay, so what do you get? Well, you might ask, do I need this +1, right? Can A gamma just interpret C gamma? And unfortunately, it can't. So C gamma will be able to prove truth predicates for transitive sets, and A gamma doesn't do that. And in particular, C gamma will prove that there is a transitive set model of A. So also satisfy foundation. Okay. All right. So using fixed point, you can now show that for any ordinal alpha, the constructible universe up to alpha exists. So you can define L. And then pairing this via the star translation, I'm probably going to write these out because we also have to make some observations. So gamma 0 or cofinality, countable cofinality, what we get is we're going to get that here, B gamma plus sigma, K plus 2, separation interprets C gamma plus sigma A plus 1, a strong collection. So strong collection essentially, well, if you don't want to bother with, there's a similar notion in arithmetic. Basically, I can bound even partial functions. So collection, you need the functions to be total. For strong collection, you need the functions may be partial. If you, or equivalently, you can see this as being sigma k plus 1 collection and sigma k plus 1 separation. Okay. So strong collection plus, B equals L. And then similarly, we get for the delta case, right? What we're going to get is sigma k plus 2 separation, delta k plus 2 separation will interpret C gamma plus, and this time it will only be sigma k plus 1, just weak collection. On the other hand, when we get to gamma, successor, or gamma of cofinality greater than omega, what we're going to get is, well, we're going to get essentially the same results, but with plus 1. So maybe I'll just write it. Plus 1 separation. And you might wonder, what about the limit cases? So what about the cases with k equals 0 and you get funny stuff? So even in the case when you start with, well, with delta 1 separation, you actually get it. Let me just write this. And then you get similar results here. E gamma plus sigma k plus 1. Apologize for the bad handwriting. So what do we want to observe is that, well, clearly, in this case, we cannot do better when the cofinality is this, because these are essentially the same theories plus axiom beta, so it's a strictly larger theory. But what about here? Can we do better? And there's one last thing to observe. You actually don't get sigma k plus 1 reflection. This was proven by Mackenzie. You actually need sigma k plus 2 induction on the natural numbers. And we'll discuss about that. So what about the cofinality gamma case, right? We still have this loss. For gamma equals 0, we know it's necessary, but we also have that it's going to be necessary for limit ordinals with countable cofinality. Okay, let's observe. So in the other cases, what we had is that the countable sets could be coded as elements of P gamma. However, what you have is that given a countable set in here, right, given a countable subset of P gamma omega, that, if I take the union of that, will give me an arbitrary set of P gamma plus 1. Why? Because I can fix a countable, maybe I can actually briefly sketch why this is true. So maybe with V alpha, it's a bit, P gamma might be a bit more intuitive. So what do we have? Is imagine if we have some subset, and then we have our cofinal sequence, right? Alpha n plus 1. Well, what do we have? This set, a subset, right? So we have this subset X, right? X is going to be a class in V gamma. Well, this X here, right, can be written as X intersect V alpha n, which is going to be an element in V alpha n plus 1, which is, in V gamma. This is a standard way. Any set is going to be the union of some countable set of elements, essentially. But what does this mean? This means, and we're now working over V equals L, so we have all the choice we want. And so what we are going to do is that if we can carry out essentially the same Kleene normal form theorem, right, for formulas which are pi11 set, right, over p gamma omega. And that means that we can express something being pi11 over v or over p gamma omega as being well-founded. And what does that mean? So if you actually look at Simpson's book and how he carries out, he shows that not only do you get that for any formula phi, its translation is going to go down, but you also get the inverse, right? So any sigma k plus 1 formula, right? Sigma 1 n plus 1, sigma 1 n plus 1 formula over p gamma omega, well, this is going to be expressible by a sigma n formula over this theory. But what does this mean? This means now what I can, just straight up, we get that since the external universe satisfies sigma k separation, we're going to have that the gamma plus 1 power set of omega, and this is going to be a proper class, satisfies sigma k plus 1 separation. To be more specific, C gamma plus V equals L plus sigma k separation proves that for any instance of sigma k plus 1 separation, it restricted to P gamma plus 1 omega. Okay, and then what do we do? Well, we want to get back to B, but we already have a translation for like weak systems like A gamma. The only axioms that might be an issue are pair and union, but pair and union were only needed to define the coding on P gamma omega. So what you can actually do is just carry out this B star translation that we mentioned before, and this will give us an interpretation to PK plus 1 separation. So actually what you get, and this should be just a K, and this could be a K plus, just K plus 1, you get this interpretation, so you get back. So this is the best you can get. Probably a few things to mention. This has gone on for quite a while. So some limitations. So what we have is that going from high separation to lower separation, you prove the consistency, so you can't get the inverse interpretation. Yeah, so you can't get interpret more separation. You can't, you can't even get more separation even if you work with collection and axiom beta. And then what you have is that if you go down ordinals, so you work to a lower ordinal, then you can interpret the system with full comprehension, full separation and collection. Okay. Finally, what about the delta n cases? So the delta n cases, just as in the case of second order arithmetic, so delta 1,1 comprehension is actually pi12 conservative over ACA naught by the Barwise-Schliff theorem. And similarly, I mean, comprehension in like the finite case is, induction. So what you actually have is that, there's conservativity results between, induction for delta n plus 1 formulas over induction for sigma n formulas. So this persists even at higher levels, which is quite nice. This was all shown by essentially shown by Mackenzie. They work with end extension of models, and you can sneak in a lot of power sets and still do the construction. So we get the same conservativity results for the delta n case. They express it in terms of collection, but then if you manage to read this, you're going to get that. This is like over KP, right? Sigma k plus 1 collection in KP implies delta n separation, right? You get, I think, huh?
What is KP?
KP is KP. Sorry, it's Kripke-Platek. Yeah, it has sigma 1, but oh right, this should be KPR. I'm using Mackenzie's notation. That's true. With foundation, this is false. This is really false. That's correct. And in fact, once you have induction, it explodes. Sorry. Yes, this should be KPR. That's correct. But over even KPR, if I have sigma k plus 1 collection, that implies delta k plus 2 separation. And in particular, what you have is, well, you get analogs to the Barwise Schliff situation, even at these higher order systems. With induction, then you get so with induction, what you get is that the systems become a lot more complicated. So, for example, if I start adding like even pi 1,1 induction over delta 1,1 comprehension, it no longer remains conservative or AC naught plus pi 1,1 comprehension. In fact, it implies AC naught plus. So it proves the existence and the consistency of AC naught plus full induction. So it's the situation changes a lot once you add induction to these systems. And then
what's KPR?
KPR is KP, but instead of the scheme that states that for any formula, it either defines an empty class or a class that is well-founded, so has a least element. It just has the axiom of regularity that states that any set is well-founded in terms of sets. Yeah, so like KPR is going to be conservative over AC naught, full L2 conservative over AC naught. That was a result by Jaeger. And in fact, but the moment you add like even full foundation, it explodes in complexity. Okay. Solidity and tightness. So these are some notions that were developed. So these are some possibly final considerations about these systems, right? We want to maybe consider ZF minus plus the iterations of the power set. Are they solid or are they tight? There was a bit of a search for a while whether there were some strict subsystems of ZF that had these categoricity-like properties, and in a sense would kind of say that ZF was in a privileged position in terms of its meta-mathematics. I think that was proven not to be the case, but this was something I looked at a year ago before we knew there were strict subsystems which are solid. Well, what is solidity? So solidity is essentially, well, probably we should start with tightness, okay. So a theory T is tight if for any pair of extensions of T that are bi-interpretable between each other, then they must coincide, right? So the classic example, the classic example is going to be like PA, okay. And I think this was like first looked at by Visser. So we say Visser actually shows that PA satisfies this stronger notion. So a theory T is said to be solid if for any three models, such that we have this chain of interpretations. So M0 is going to interpret M1, and M1 interprets M2. And we have that M0 is going to be definably isomorphic to M2. Then we have that M1 is also definably isomorphic to M2. And the idea you can, well, how does the proof that PA is, last board, okay. How does the proof that PA is solid work? Well, imagine if I have some model, M0, it interprets some model M1, right? This M0 is going to, by induction, embed as an initial segment of M1. And then what do we have? Well, we have that M1 is going to interpret M2, get rid of this, is going to interpret M2, and it must embed as an initial segment. But then what do we have? We have the definable isomorphism of M0 and M2. So M0 is actually going to turn out to be an initial cut of M2, or of itself, and that contradicts induction. You get similar, so I now showed that there's a way that, for example, I start with some theory, I take, the second order version of it, like Z2, and that will always be solid. So if the initial theory is solid, then going up to like Z2 that will work. So NBG is not going to be solid, but Kelly-Morse is the analog, the higher order version. And okay, so we have these solidity examples, and solidity implies tightness, okay? Solidity implies tightness because if I get two extensions, U and V, that are bi-interpretable, then all of its models will bi-interpret each other uniformly. And then you can do this argument to show, well, the models are going to be all isomorphic, so they must be the same theory. Okay, final point. So the only thing we kind of observed that were two. You can use the NIAT results to show that certain, like ZF minus plus the nth power set exists, plus the universe, everything in the universe has an injection from the nth power set, a partial surjection from the nth power set onto its transitive closure. Well, that also is going to be tight just because of bi-interpretability results. So we get that, sorry, maybe I should mention this. If T is solid or T is tight and is bi-interpretable with some theory S, then S will also be tight or solid respectively. Just by interpretability, you do like a little diagram chase to convince yourself. Okay, so Hampkins and Freyer show that when power set is absent, this does not hold. So they actually have this very nice construction. So what I do is I take a model in which the continuum is, I don't know, Aleph 2, for example. I take Martin's axiom, and then I take the existence of a definable almost disjoint family of size Aleph 1. And what I can do is, in this setting here, you can get a nice bi-interpretation between the hereditary countable and the hereditary Aleph 1 sets of the universe. And the construction is quite nice. There's no natural analog of MA for higher forcing in general. You just don't get it. But actually, and there's not much insight in this. You do, however, get it for the almost disjoint coding. So you can essentially just get the result and add a gamma before it. It's not much. It's yeah, okay. So in particular, you can then construct in the same way two theories that extend ZFC, ZFC plus the gamma F power set of omega exists, and you can show that they're bi-interpretable, but they're distinct theories. And finally, last observations. So I mentioned this before, and also decent on time. So we have that A interprets B, but you need delta zero fixed point to interpret C. And in general, what you have is that, well, right, A is very analogous to our systems A and B, right? ACA naught is very similar to these two systems. And ATR naught is, very similar to this system C. And ATR naught is strictly stronger than ACA naught, right? It's a stronger system. It proves there's omega models. There proves, a lot of things. And so in the gamma equals 0 case, we have that, ACA naught cannot interpret ATR naught because, and maybe this is something, right? For any I never mentioned this, and it's not completely trivial. A theory T cannot really, any reasonable interpret, T cannot reasonably interpret any theory, like I delta 0 plus gamma 1 plus consistency of T. Right? Any reasonable T and any reasonable interpretation. And you kind of have to work it, you can't get this to happen, right? And the main reason, maybe leave it as something to think about. But anyways, so what can we get? So since ATR naught proves the consistency of ACA naught cannot prove ATR. So in particular, what we have is that just B in general will not be able to interpret C because B is mutually interpretable with ACA naught and C is mutually interpretable with ATR naught. Okay. Sure. Okay, but then how do we prove this for, what if you add gamma? So what if already at the level of the reals, right? Things work differently, right? Being well-founded is no longer pi11 complete. So the type of arguments have to be a bit more subtle. But however, there's a nice way of being able, via trees, right? I can construct a sufficiently, given a set X, I can construct a large enough tree of sequences such that the unique bisimulation will actually will actually, compute or define in a delta zero fashion the theorems of X as a transitive set. And the construction is a bit involved. Yeah, maybe I'll leave it at that. So thank you for your attention.